Let's start. As always, any questions, any comments, please post to the chat or raise your hand, and Daniel hopefully will be able to monitor and either answer you, as he seems to have been doing for most of the questions, or alert me if he wants me to answer, and I will take it. So today, we're going to finish discussing logistic regression. So obviously, we didn't have a class on Monday, but last week we started discussing logistic regression. We went through most of the stuff on logistic regression, and in fact, you are working on a logistic regression problem in the problem set. But we didn't finish discussing how to extend logistic regression to multiple classes. So all of the discussions we had so far was on 2 classes, and today we will extend it to more than 2 classes. So that will be the first part of today's lecture, and then we will move to another supervised classification method. So again, we are talking about supervised learning, and within supervised learning, we did a small detour to regression, but most of the focus is on classification. And the next method we'll discuss is support vector machine, which also uses ideas from regression to do classification, and we'll get to that and what's the difference between using support vector machine and other methods. Okay, but let's start with, or let's conclude our discussion of logistic regression before moving on to the next topic. So for those of you following the slides, this is still the slides on logistic regression that I posted a week ago, 2 weeks ago. Okay, so just a short reminder, I won't go into the full discussion that we had last time. But generally, if you remember, we defined a probability function for 2 classes. So the probability of y given x, we said logistic regression is not a generative model, so it doesn't tell us how to predict x given y. But since our goal is to predict the label, this is definitely something logistic regression provides, and we defined it as 1 over 1 plus EWTX for y equals 0, and 1 minus that, which is e to the power of WTX over 1 plus e to WTX for class 1. Okay, so this is a probability, and we showed last time that this is a valid probability, so it sums to 1. It's always between 0 and 1. Right, it's two events that have to be, the sum of these 2 events is 1. So this was a valid probability function, and we spent most of the class on trying to learn or trying to discuss how we learn the best values for W for a specific input. That was the major focus of the logistic regression function. A class, and we said we can do it with training. Of course, we need training data, but once we have training data, we can do it with gradient descent or gradient ascent for the maximum likelihood estimation problem. Okay, so and then we discussed a little bit about gradient descent. But generally speaking, we define this as a 2-class classification problem where the probability for one class is always 1 minus the probability for the other class. What do we do if we have multiple classes? So, right, I mean, all of the classifiers we talked about so far, and that's not trivial, because when you will talk about support vector machine, you will see that that's not always the case. But most of the classifiers that people use can be applied to multiple class labels, right? For example, if you want to predict cats, dogs, horses, and cows, right? So you don't just want a binary classification. And we talked about how to do that for decision trees, k-nearest neighbors, a naive Bayes, neural networks can do this. A lot of methods can do this. What about logistic regression? So it turns out that logistic regression can be naturally extended to more than 2 classes. And I will show you in a second the definition. The important thing to understand is that this, of course, requires to learn more parameters. Basically, any number, the number of parameters, we need a special set of parameters for each of the classes except for the last one. So for example, in the binary case, we have 2 classes. We have W's, which we can associate with class 0, and we don't have parameters for class 1, right? Because 1 minus that is the probability of class 1. But when we have 2 classes, when we have 3 classes, we are going to have another set of W's for class 0, another set for class 1, and for class 2 we are not, because we are doing 1 minus the probability of the other. So the more classes we have in a logistic regression problem, the more parameters we have, and these scale linearly with the number of of classes. Okay, that's the basic idea. Let's see what's the definition. So if we have a multi-class classification problem, we can define P of y equals I, given x for all i's that are less than k. So k is the total now. Let's say k is 5. So for the first 4 classes, okay, we define it as some function, right? The logistic regression function with parameters w0, w1, and I, right? So for class 0, we have w0, 0. For class 1, we have w1, 0, and so forth. So each of the first 4 classes has its own set of regression parameters. In this case, logistic regression, but w's that we need to learn. The last class does not have its own set of parameters because the probability for that class is 1 minus the sum of the probabilities for all the other classes. Okay, so this is the definition, right. Basically, by doing this, we guarantee that the probability remains between 0 and 1, always sums to 1, just by defining this. This is always positive, obviously. So right, we can't have a negative value for this, and the fact that this requires that this is the probability of the last class basically guarantees that everything will sum to 1. Okay, so this is just the definition. Now, so this is the definition, and using that we can scale up to any number, of course, of clusters that we want. The big question for us is how do we find the parameters for this, right? Because now we have, rather than just W0, W1, W2, we have much more parameters than before because we have a set of regression parameters for each of the classes except for the last one. Just a note that right, so right, for the last class we have the probability is 1 minus the sum of these probabilities, and basically this is the right. Right. So this is basically the probability of the last class. So this, I mean, right, it's easy to see that this is a valid probability. This is always between 0, this is always positive, this is always between 0 and 1. It sums to 1 if you just sum over all the classes, and everything should hold. And then the other thing I would say is that a binary regression is just a special case of this where k equals 2. Right, then we have values for the first one. Okay, so this is the definition, and the question, of course, is how do we learn the parameters? And it turns out that we can learn the parameters exactly the same way that we did for the binary logistic regression problem. In other words, we do it by taking the derivative with respect to each of the different parameters. Now we have, rather than, let's say we have k classes, then instead of, let's say, m features, then rather than having m or m plus 1 parameters, we have k minus 1 times m plus 1 parameters, right? So we have more parameters, but each parameter has its own meaning. So one is for this class, this feature, and so forth. So we can take the derivative with respect to each of these parameters. When we do that, it comes out, and you can do it. It's not actually a very big, or it's not much different than what we did for the 2 classes, right? So basically each parameter is only affecting its own class and the last class. It's not affecting any of the other classes because the last class is a combination of all the classes. And basically when you take the derivative, you see that basically what you get is very similar to what we got in the binary case. After cleaning it up a bit, it's basically a delta m of yi. Basically, delta m means that whether a sample I belongs to class M. Okay, so this is 1 if it does belong to class M, and 0 otherwise, minus the probability, basically the error that we have, right? Because if sample 1 really belongs to class M and this is very high, then the error is low. If sample 1 doesn't belong and this is very low, then again, the error is low. And if sample 1 doesn't belong, but we predict that it does, the error is very high. So this is the same we defined for the 2 classes, but now applied to multiple classes. And again, there's no closed form solution. So we do gradient descent or gradient ascent in our case, because it's a maximum likelihood problem. And we get this optimization function. And again, I mean, different ways of doing it. Stochastic, which we mentioned last time, which does it based on 1 sample at a time, or batch, which does it on relatively small number of samples, or global, which does it on all the samples together. It's up to you. and there are different advantages or different disadvantages to each one. But the important thing is that this basically will generalize. It's basically the same algorithm to compute or to find out the values of the parameters. Of course, when we have more classes, we have more parameters, it might take more time or more iterations for this to converge, but other than that, it's the same. Okay, so basically a logistic regression can be applied, and in fact, in many cases, it is applied to multiple classes. And logistic regression, unlike, for example, naive Bayes and single decision trees or k-nearest neighbors, which are important to know, and we said already that a lot of methods extend them, logistic regression is still a pretty popular and successful method. So even though, you know, it's not the newest method and it doesn't work the best in some cases, it's something that is pretty easy to implement, very general, and works pretty well. And as you will see in neural networks, it's basically, or a lot of the ideas in neural networks are based on logistic regression. So the sigmoid function plays an important role in all the ideas of gradient descent in neural networks as well. The last thing I want to say about a logistic regression, although again we will talk much more about it for support vector machines, is that everything we said about transformation of the input for linear regression applies the same for logistic regression. So even though we treat the input, or until now we treated it as basically working on the values we obtain as input, any transformation of the input that is a fixed or deterministic function can be used as features, right? I mean, as long as you apply to all the training and test data, from the point of view of the algorithm, this is just inputs. So any transformation, if you want to take a univariate and make it into a polynomial, as we show in the linear regression, or some other transformation, a Gaussian transformation, whatever, you can still do it with logistic regression. Again, all the caveats we said apply here as well. The more transformations you do, the more parameters you have, the more data you will need probably to reduce overfitting. But other than that, everything we said would work on transformations. And you can choose whatever transformation you want based on what you think. Okay, so that's it for logistic regression and for multi-class logistic regression, which is, as I said, something that people still use a lot. In fact, we use it in our research, and I know that other people are using it. It's pretty quick to learn and works, unlike naive Bayes, which is really, I mean, it's a nice idea, but it's very naive, right? Because in practice, things are not independent. Logistic regression seems to work still pretty well. And again, extensions like neural networks work even better, but that's also good. Okay, good. So if there are no questions, then we can move to the next topic, which is support vector machines. And I don't think that are questions. Okay, so let's talk about support vector machines. Okay, so support vector machines are by far the most interesting algorithms, at least in terms of their name, right? I mean, this is for someone who hasn't seen support vector machines, the name should sound intriguing, at least. I mean, neural network, I guess, is also intriguing, but by now, probably everybody knows what they are. So if you haven't heard about support vector machine, you might find the name intriguing. And of course, one of the first things we'll do is we'll explain what does a support vector machine, or why do we call this method support vector machine. But basically speaking, support vector machine is a classification method. Although it can be used for regression, it's not designed for regression like decision trees. People use it for regression, but it's not really designed. And a lot of the discussions that we're going to, or a lot of the things we derive are not intended, at least for regression. So support vector machine is a classification method. And in addition, and this is something that that should be emphasized, support vector machine is a regression is a classification method for a problem with two classes. So it's not trivial, although it can be done. We'll talk about it, to extend support vector machine, unlike almost all of the other classifiers we learned, to more than two classes, because the way we define the optimization function is really dependent on this idea of two classes. And again, there are ways to extend it. We'll talk about it, but they are more heuristics than actually derived methods. Unlike, for example, the logistic regression, where we actually derive the solution for multi-class classification. Suppose vector machine, like logistic regression, like decision trees, is a discriminative method. So it's not even probabilistic. So it's not trying to compute the probability. The only thing it tries to do is to tell you if this sample is in class 0 or class 1. That's the basic idea of suppose vector machine. And I think I mentioned it, until neural network came and really beat out everything else, support vector machines were the best method for classification, except for the aggregate method. So we talked about bagging and boosting. Oh, I didn't talk about boosting, but I mentioned it, bagging and random forest. They can work, the ensemble methods usually work better than the individual methods. But if you looked at individual classification method, including naive Bayes, everything we talked about so far, logistic regression, naive Bayes, and so forth, support vector machines were the best. And one of the reasons why they were the best is because they were very, very flexible. And we'll see later in the class what is their flexibility, but also because the optimization function or the data or the parameters they're trying to learn may be actually, or the thing that it tries to optimize may be a good thing, right? So we will discuss it, but at least empirically, it seems like whatever it's trying to do is an important goal because it works very well, at least as a standalone method compared to other methods. So this is again, comparison from several years ago, but still a valid comparison for the methods, except for neural network, which since then have been greatly revolutionized. But all the other methods, more or less, are the same. Okay, so this is support vector machines. Before neural networks were neural networks, so before 2010, 2012, support vector machines were the big hype in machine learning. Nowadays, they don't get a lot of credit. Yeah, people still use them, but it's not but you know, when I started teaching machine learning, they were all the hype. Not anymore. There were actually classes just on support vector machine and kernel spaces, Hilbert spaces, and so forth. I don't see as many classes today on that, but I do see a lot of neural network classes. So apparently, the crown has been moved to neural networks. And let's see, you know, as I said, let's see when you guys teach machine learning, what will be the method that will be the most attractive then, but you know, we'll find out, I guess, in 10 years. Anyway, so, but still, I mean, it's still a useful method, and like logistic regression, people use it quite a lot. Again, one of the main reasons is because it's very flexible. You can do a lot of things with it, as we'll talk about. Okay, so but before we jump into, you know, why it's good or you know, how well it works, let's just define the optimization function. Of course, the goal is to do classification, but how we are trying to do classification and try to motivate why this makes sense. Okay, so we are still at this region of or general theme of regression-based classification method. So regression means that we have some function of parameters multiplying the inputs or transformation of the inputs, like we did on logistic regression, and we defined right. I mean, in the start of the logistic regression class, I mentioned that we can actually have a line based on just the linear regression, not even the logistic regression, that will work, at least in some cases, to classify the data very well. For example, in the data that I'm plotting here, right, so blue dots and red dots, the line that I'm showing you here is basically perfectly going to classify the points. So some points are on one side of it and some points are on the other side. So it's a perfect line. And if we actually solve the optimization function, and that's right. I mean, there might be, but this is pretty, this can be, again, maybe slight difference, but this can be pretty a reasonable outcome if we optimized just the regression method. So the regression basically, the regression model will say that all the values here should be 1 and all the values here should be -1, okay? And then we try to solve it with a line, and this is maybe one of the lines that we will see. I mean, it could also be a horizontal line. It depends on slightly, but let's assume that this is the line that we get. I mean, we get something. So this is a perfect classification line. It works very well. But it's not the only perfect classification line, right? If I move this line a bit here, or a bit here, or a bit here, or a bit here, it will still be a perfect classification. If I change the degree or the angle, it will also be a perfect classification. Why do we get this line? Why is the line here where it is, rather than at other places? If we solve the regression problem, can anybody tell me? Why is the line where I put the line, basically? So what drives, right? If I mean, that's maybe harder to explain, but you know, what drives the exact location of the line? So we know that the line has to be, let's say, a good line will be between blue and red. But what drives the exact location of the line in this case? That you know, may or may not be a good idea, but it definitely happens here based on the optimization function we're using for regression. Yeah, so we are doing least square minimization, right? And the answer, right? So the answer from Joseph is the one I was looking for, and indeed that's what I was trying to emphasize. If you look at the points here, you see that the blue dots are a bit more spread out than the red dots. And the line is trying to basically be as close as possible to both points, but because the blue dots are slightly farther from the line, it moves closer to the blue dots than the red dots. In terms of classification, it doesn't matter, right? But in terms of the line itself, it would matter. However, there are, of course, a lot of other lines, right? So the line is closer to the blue because it tries to be as close as possible to as most point as it can. However, there's lots of other lines that will do the same or will perfectly work on the classification. And we already said that logistic regression is identifying, you know, in this case, it's not a linear line, but it's identifying a logistic line that does a very good job at classifying without caring too much about the distance from the points, that as long as it classifies them correctly. But what if we want to stay in the linear space? So logistic regression works well, but it's not working in the linear space, right? Logistic regression has this logistic space. What if we want to stay in the linear space? Can we define a target function that will lead us to find the best line in terms of discrimination, not in terms of optimizing the distance, which we don't care, because as long as we get the point correctly, why do we care about the distance? The only thing we care about is accuracy. Can we find the best line using regression model, but not optimizing the least square, which doesn't seem to be a good idea for classification, some other optimization function, and still get a good linear line that separates these two? So again, it's not always possible. Sometimes there's no linear line that separates the point, but there are cases where there is, right? And this is an example of a case where a linear line would be a good way to separate the points. But if we just use the linear regression method or the optimization based on least square, we wouldn't find a line that is maybe the best. This seems to be a better line, right? Because it's roughly halfway between all the the closest blue point and the closest red points. This line that is basically as close to any point on one side as it is to the other side, right? So basically what this line does is it doesn't try to be close to all the points on both sides. What it tries to do is to be as far as possible from the closest point on either side. Basically to provide the biggest margin. Margin is the distance between line and points from both sides. So the margin is defined as the distance from the line to any of the points. So obviously, because we are doing two-class classification problem, you will have one point that is the closest on one side and one point that closest on the other side. They have to be the same. If they are not, then moving it slightly in one direction would make the margin bigger. So when the margin, right, when the margin is optimal, it has to be symmetric for the closest point on both sides. Everybody hopefully sees that. But that's just a minor comment. The more important comment is that if we agree, so we can do the optimization based on least square, but it doesn't seem to be a good idea. So margin is another idea of doing the optimization. It doesn't tell us how to find the values, but it's just a conceptual idea of saying that rather than minimizing distance to all the points, the goal of the linear line, the goal of the linear line is to maximize the margin, basically to be as far as possible from any of the points. And still, of course, get the classification correct, right? I mean, I can put the line infinity and it will be very far, but that's not going to help in terms of classification. So the goal is to get the classification correct while being as far as possible from any of the points. Okay, so this may actually be on average very close to 1 point. In this case, the line is on average closer to the red points than the blue points, but we don't care about that. The only thing we care about is the points that are closest to the line. Okay, so this is called the margin. And the goal is to find the location or the line itself that will maximize the margin. Okay, so the margin in this case, you can see it as yellow. This is the area that does not have any point from either side, and the margin is symmetric. Because, as I said, if it's not symmetric, then moving it slightly in one direction or the other will lead to a bigger margin. Okay, so this is called a margin, and the goal of support vector machine is to find the max margin. This is why it's also called a max margin classifier. So as we said, again, rather than doing least square, which takes into account all the points, right? I mean, the sum of the distances from all the points, max margin classifiers only focus on a small subset of the points that define the margin. If I add a new point, right? If let's say, just to illustrate this. Let's say I'm doing this this classification problem, and this is the line that I find, right? Now, in least squares, if I add another point, it's going to impact the line because the line takes into account all the points. In max margin classifier, I can add this point, the line doesn't move at all. It stays the same because the margin is not affected even if I had hundreds of points here. But if I had a point here, it might move the line because now I want the line to move slightly. That's the idea of max margin classifier. Okay, so it's affected by the classification, but not by all the points, just the points that are closest to the line. Of course, we need to define what these points should be, and it's not really, I mean, I didn't say how we find it, but once we find it, the important thing is that whatever we find is only affected by a small number of points, and these are the points that are closest to the lines. Okay, so this is the idea of max margin classifier. Now, this seems like a good idea, but of course, I haven't theoretically showed you that max margin will be the best method for classification. It definitely seems like trying to optimize distance from all the points does not make sense. We already showed several examples where the target function for linear regression is not a good idea. But I haven't proven that max margin is the best thing to do. Okay, so but still, let's try to, or if we assume that it is, then most of the rest of the lecture will be about how to find it. But in practice, the reason why people like max margin is, first of all, it's intuitive, right? It makes sense that we want to have the line as far as possible from both of the classes because we don't care about getting one class right or the other. We care about getting both of them right. There is some theoretical support, but more importantly, this works very well in practice. So when you try max margin classifier or support vector machine, they seem to work extremely well. Again, there are other things that work in their favor, but basically the idea of max margin is a proven idea. Okay, so from now on, we assume that max margin is a good idea, and the question is how to find it. We won't explain why max margin is a good idea. Okay, so the motivation is that, you know, it seems like a good idea and it works, but I'm not proving that this is a good idea. Okay, so if it is a good, and the last point before we go into the methods or how to find the max margin is the name. So this specific example that I've shown you, where we try to find a linear line with a different optimization function, not with regression, with a different optimization function, is known as linear support vector machines. Why is it called support vector machines? What's the name? The name comes from the fact that only a subset of the points support the line. Support means impact the line. As I showed you, I can add a lot of other points, they don't have any impact, but there are a few points that do define the line. These are the points that basically are with the minimal distance to the line. And these are called support vectors. These are the most important points, of course, in our sample because they affect the boundary. There's lots of other points that don't have an impact on the line. Okay, at least in the linearly separable case. And so this is why it's called support vector machine. Support vectors are the points that support it machines. It's just to show that this is an automated method. But the support vectors are the points that basically define the margin, or the ones that the margin is closest to, which basically is what the margin is defined by. Okay, so this is support vector machines. This is the name, and the idea, as we said, is to find a solution that maximizes, or to find the line that maximizes the margin. Okay, so this is the setup for the problem. The rest of the lecture, or at least for today, most of what we will work on is how to basically find this line. Okay, so a line, by definition, is a set of parameters, right? So a parameter multiplying, in this case, in the one-dimensional space, it's two values, but in higher dimensions, it could be multiple values. So the question is, how do we find parameters that will lead to the max margin separation? Okay, so for that, we need to somehow connect the max margin to the classification outcome. So let's see how we do it. So this is, again, this is the setup of our problem. Right? This is the linear classification problem, but now rather than optimizing distance, we optimize accuracy. And we maximize the margin while trying to keep, of course, we try to optimize or keep the accuracy perfect, basically. So I should say, that's a question that maybe you asked, or maybe you haven't asked. I'm going to assume for the next few slides, at some stage I will relax that assumption, but for now, I'm going to assume that the problem is linearly separable. What does it mean that the problem is linearly separable? There is a line, or there is a plane that completely separates the two classes. In fact, there's infinitely many of them, and our goal is to find the best one. But we are assuming that they are separable. Sometimes, in most cases, they are not separable, right? In practice, it's very hard to find a line that separates samples in the two. So we will deal with that if it's not separable. But for now, let's assume that they are separable. Okay, so if they are separable, then there are lots of lines that can separate them. We already showed that. And our goal is to find the line that, first of all, separates them, and second, leads to the max margin. Okay, so let's say that this is the classification problem, right? So this is the line, and this is the margin between them. So if we say that WTX plus B is less than -1, we predict class -1, and if it's greater than 1, we say it's class 1, and in the middle there shouldn't be any point. This is the margin. Okay. Now we selected 1. 1 is an arbitrary number, and I will get to that maybe later. But for now, we are selecting 1 as the distance between the closest point and the line. The actual value doesn't really matter here. So you could select, okay, we'll see that. Okay, so if that's the case, then we are trying to find a line. So basically, we are trying to find a set of values, W and B. B is the parameter for the bias parameter, and W are the parameters multiplying the input. We are trying to find parameters W and B such that, first of all, for all points in class 1, we want WTX plus B to be greater or equal to 1. For all points in class -1, we want WX plus B to be less than -1. And between -1 and 1, we don't want to have any points. We know there is, because we assume it, we know there's several, in fact, infinitely many lines that can guarantee this. The question is, which line do we want to find? And the answer is, we want the line that maximizes. So I talked about the linear separation, and we'll get to that. So we want the line that will maximize the margin between these two. So the line should satisfy both correct classification. So all points in class 1 should be greater than 1. All points in class -1 should be less than -1. We are guaranteed that such line exists. But in addition, we want to have the width, the distance between the decision and the boundary for class 1 and class -1 be the maximal that it can. Okay, so the question for us, so we already encoded the accuracy with the parameters. So we want WTX plus B to be greater than 1 or less than -1 for different classes. That's good. So we are able to connect W to the classification outcome, but we haven't defined how to link the margin to the parameters, right? In order to maximize the margin, we need to have it as a function of the parameters. So how do we write the margin as a function of the parameters? Right? Again, in linear regression, we had the least square. So we link the optimization function to the parameters using, wx plus b minus y squared. How do we do it for the max margin classifier? So for that, we need to start with a few observations, and then we will use them to derive basically an optimization function that will lead or will help us find the max margin classifier. So first of all, we observe that given our definition, just based on the definition, we can say that if we have basically a line or a plane, right, in high dimensional space that defines the class 1, right? So the points on that plane are the closest to the margin for class 1, and all the other points are below them, right, are farther away. If we have such plane, and this could be a 2D plane, or it could be a much higher dimensional plane, or it could be a line. If we have such plane, then W, the vector W, which is the parameters, is orthogonal to that plane. What does it mean orthogonal? It means that when you multiply a line, if you have a line on that plane, right, any vector on the plane is defined as the distance between 2 points on the plane. When you multiply a line defined by 2 points on the plane by W, you get basically 0. Okay, so W times any, so orthogonal means that they are 90 degrees in some sense. Okay, with all the points on this, with all the vectors, sorry, in this plane. So a plane, a vector defines a plane because it goes just on the plane, it cannot go in and out. And W is orthogonal because any vector on the plane times W will be 0. How do we show that? Well, we just use linear algebra in this case, and we know that each line on a plane or on high dimensional space is defined by 2 points, right? So 2 points define a line, of course, in 2D, but also in higher dimensions. So if we take 2 points, let's say U and V, that both reside on the +1 plane, right? They define U minus B is a line. And when we multiply U minus V and by W, we get WTU minus WTV. We know that WTU equals, in this case, it's 1 minus B because it's on. So again, remember, I should say, this is points on the +1 plane. +1 plane is the plane where points that are closest to the boundary, to the margin reside, to the boundary reside. Okay, so all the points on that plane, they don't have WTX plus B greater than 1. They have exactly equals 1. Okay, if they were greater than 1, then we can move the boundary a bit more and have it even higher. So we know that points on the plane that define, and we know that there's at least 1 point there. If there wasn't a point there, you wouldn't, right? I mean, there are multiple points, of course, infinitely many points. But from the sample, we have at least 1 point there. Otherwise, we wouldn't have that as the plane. Anyway, so we know that if we have or we don't know how to find it, but if we had a +1 plane and we had a W that maximizes the margin, then it would mean that W times any vector on that plane, which is defined by distance between 2 points, is 0, which, right, because WTU is 1 minus B, WTV is also 1 minus B, so this minus this is going to be 0. So this means that the two vectors are orthogonal, and if they are orthogonal, right? If they are orthogonal, it means that basically, so in this case, W is orthogonal to 2 points on the plane V, and if it's orthogonal to any 2 points, it will be orthogonal to the entire plane. So any vector is defined by 2 points, and we can do it for any vector and show that it's orthogonal to that. Okay, so this is just an observation, but of course, if this is true for the +1 plane, it's also true for the -1 plane. So whatever we said about +1, points on +1, it's also for class 1, it's also true for points in class 1. Okay, so this is straight derivation. And now we are getting into something a bit more interesting that can tell us a little bit about the distance between the 2 planes. If I take a point on the +1 plane, there must be a point on the -1 plane that is the closest to that point. I mean, by definition, if I take, I mean, they have to be parallel to each other, because we know that the distance between the plane is fixed, right? It's always the margin. That's the distance between the +1 and -1 plane. So if I take a point on the +1 plane, there's going to be a point on the -1 plane that is the closest to that point. Which point is that going to be? It's the point defined by a vector with 90 degrees or orthogonal to the point that I took, or to a vector defined by the point that I took on the +1 plane. Okay, which vector is orthogonal to that to this point, or to any point on the +1 plane? It's W. So if I take a point on the +1 plane, I take W, then at some, and I go, W is just the direction. It's a vector. I go along the direction. I will get to the -1 plane at some stage, because I'm going 90 degrees. And when I get to the -1 plane, I'm guaranteed that I will get to the closest point to my point, because we have a 90-degree angle both in this plane and in this plane when we are going with W. The only thing I don't know is what's the distance between these two. We haven't defined that. But if we use W, we know that W is basically connecting the two planes, right? And we have to travel using W some distance. Let's call it lambda. I don't know how long. We haven't, but that's just an observation about distance, right? The distance is defined by a 90-degree angle from both planes in this case, and W is the vector that satisfies this. So of course we don't know lambda, but if we knew lambda, it can give us some information on the margin, because lambda W is exactly the distance between the two planes, right? But of course we don't know. Okay, so these are observations. It doesn't tell us still what the optimization function is, but it's helping, or it moves us in the right direction. So now let's use this observation, especially this one, that the distance traveling from point on the +1 plane to the closest point on the -1 plane goes along W to derive the max margin optimization function. Okay, so this is the information we already have. So we know that W for a point on the +1 plane, right? If I take X plus, which is a point on the +1 plane, because it's on the +1 plane, we know that WTX plus B equals 1 by definition of the +1 plane and W. If we take a point on the -1 plane, then WTX minus, which I'll just select the point, plus B equals -1, again, by definition. We know that if I want to go from X plus, let's say X plus and X minus are so let's start with X plus on the +1 plane and select S minus as the closest point on the minus plane, okay? So we know that these two holds for that. The next thing is that I also know that I can get from X plus to X minus by going along W some distance. And the margin is defined as the distance between the two planes, which is just the distance between X plus and X minus. Of course, we don't know what it is. This is M. But this is the margin. That's what we want to maximize, optimize. We also want to maximize. Okay, so now we can do some algebra and try to see if we can, the goal really of this exercise is to define M in terms of W and B, right? That's the goal, because W are the parameters. We want to find a way to maximize the margin by selecting a set of parameters. So how do we define? So that will be the goal. So let's start with this. We know that WTX plus B equals 1. We can replace X plus by basically lambda W plus X minus, right? We just showed that. Now we open this up and we get WTX minus plus B, we had that before, plus lambda WTW equals 1. What is this? WTX minus 1 plus B. This is, from here we see that it's -1, right? So basically, we have -1 plus lambda WTW equals 1. And we can move this around and say that, right, lambda equals 2 over WTW. Again, that's not our goal. Our goal is to find M. But at least we were able to get rid of lambda, which is also good because we didn't know what lambda is as well. Okay? So this is where we are after some derivation, that we can actually get rid of lambda and define it using W, which is good. But we still really, our goal, as I said, is to find M. So how do we get to M? So now let's add that information to our our set of equations. And now we know that m is basically defined as the distance between x plus and x minus. Now we can use this information here, that lambda w is also the distance between x plus and x minus. Right? Remember, we said we are traveling over w with lambda, distance lambda. If that's the case, then lambda w is also the distance basically between x plus and x minus. Let's take lambda out, and now you know, w. This is right. So this is right. This is the absolute value of w, or wt w square. So we have lambda times wt w square. Sorry, lambda times square root of wt square is equal to m. And we know that lambda itself is, right, 2 over WTW. And so if we plug in the value of lambda, we get, right, this of course cancels out, and we get 2 over WTW. So M equals 2 over WTW. That's exactly what we wanted, right? We wanted to define M as a function of W, because W's are the parameter. Of course, we don't know what they are, but once we know how to define the margin as a function of the parameter, we can maximize the margin by maximizing a function of the parameters. In this case, to maximize M, we need to maximize 2 over WTW. Okay, so this is basically again, the goal of maximizing the margin is something we started with, but the way to link that goal to parameters is what we were able to derive, or what we derived by now, which is basically saying that if we want to maximize the margin, we need to maximize 2 over WTW. Okay, so this is where we are in this. Okay, so that's the goal. Now we put everything together. What we really want is parameters that do 2 things. First of all, they correctly classify the points. So all points in class 1 should be WTX plus W greater or equal to 1. All points in class -1 should be WTX plus B less or equal to -1. And they need to maximize M or maximize 2 over WTW. Or if you want, I mean, because this is a denominator and we know it's positive, we can minimize WTW. That's the equivalent, right? If we minimize this, then this fraction is maximized. Okay, so this is the way to link the accuracy and the margin to the parameters. Okay, so this is basically the problem, right? Or this is the problem we are trying to solve. So we want to maximize the margin and still get everything correct. How do we solve it? How do we find the value of W? So now we have an optimization function, right? Optimization function means that we want to maximize something and we have some constraints, right? The thing we want to maximize is this, and the constraint is that we want things to be correct. So WTX plus B is greater than 1 for class 1, less than -1 for class 2. Right? So this is the. So how do we solve it? There's lots of ways of doing it. You can do simulated annealing. You can do what we talked about, gradient descent. There are a few other methods. I'm not going to talk about all of these methods. I'm going to introduce one method that is actually much more appropriate for this specific type of problem, and we'll say in a second. But honestly, even that method, which is very appropriate for this, is not the method people use, and we'll get to why probably on Monday. But it's important to know that this can be done, but in practice, as you will see, it's not necessarily something people do. Okay, so how do we solve this? Remember, we have this constraint optimization problem. Optimization because we want to maximize this value here. Constraint because we want to make sure that WTX plus B is greater than 1 for class 1 and less than 1 for class less than -1 for class 2. So in order to solve constraint optimization problems, there's actually a lot of classes of solutions. One of them is called quadratic programming. That's a very general way of specifying constraint optimization problem where you have a quadratic term. Quadratic term means that you have a vector multiplied by itself with some a matrix R, which is an input. So in quadratic programming, the goal is to find U, which is the parameters, in our case, W, to find U, and you assume that the optimization function is defined as UTRU. R is an input. It's not something you have to find. It's given to you, but it's a matrix, basically. So this is a vector, a matrix, a vector, so you get a value. And DTU is D is again a vector. This is the quadratic term. This is called the linear term, and C is just some constant. Okay, so this is the minimization part, and this has to be subject to some inequality constraint and some equality constraint. Okay, so this is the general formulation of a quadratic programming problem. Why is it important for us to know that this formulation exists? It's important because there are very, very good solvers out there for quadratic. If you can define a problem as a quadratic programming problem, then you don't need to use gradient descent and simulator, which are general functions. You can use solvers that are specific to quadratic programming and actually work much better, usually faster and more accurate, because this is a set of problems where people spend a lot of time on trying to develop methods that can optimize the problem. If you can use gradient descent or simulator for any method, for any problem, this as well, but it's not the optimal thing, because as a general solution, it works for everything, but it doesn't work as best as the best solutions. Okay, so that's why we might be interested in trying to specify support vector machine as a general, or in terms of a more general set of optimization functions. Okay, so why is support vector machine a quadratic programming problem? What is R in support vector machine? Can anybody tell me? So R is the input matrix. What is it in the support vector machine? Let's see if people. Yeah, good. So people got it correct. So R is the identity matrix. Identity matrix, it's still a matrix, but it has 1 on the diagonal and 0 everywhere else. So basically, in this case, we get W times W, which is what we are trying to minimize. So in this case, square root, but it's also minimizing square root of WTW is the same as minimizing WTW, right? It's not, there's not going to be a difference. So yeah, so very good. R is the identity. What is D? What is D in least square, in support vector machine? Yeah. So D, again, we don't have a linear term in support vector machine. We are just trying to optimize the quadratic term. So D in our case is a 0 vector. It's still a fine. I mean, it's still, so basically the minimization is a quadratic minimization. C, it doesn't matter honestly, because it's not affecting really. I mean, we are minimizing over U. So C, we don't need to define it. In fact, in practice, it doesn't have any impact. Right, because really the only thing we can minimize is U, right? So there's no C basically. And in addition, we have this. We don't have equality constraints because we say that everything has to be greater or equal to 1 or minus. But we have a lot of inequality. Basically, for any sample, we have inequality constraints. For the +1 samples, we say that it has to be less or equal to, or greater or equal to +1. And less or equal to -1 for the -1. So basically, again, the whole exercise is to show you that we can define the optimization function that we specified for support vector machine as a quadratic programming problem. And if we can, then we can just plug it into a solver in Python, in R, in MATLAB, whatever you want, and get the solution. So this is good news. Okay. So here is the way we define it. So again, on the right, we have the general quadratic programming optimization, and on the left, so that, and on the left, we have the quadratic programming for support vector machine. Quadratic programming tries to minimize WTW over 2. Again, square root, or I mean, originally we maximized the margin, which was 1 over square root. It's equivalent to minimizing the denominator, which is the square root, and because this is positive, it's equivalent to reducing the square root and just minimizing WTW. Okay, so we get the same solution, just easier to write down. Okay, so this is the optimization part, and this is the constraint part. All points in class +1 should be WTX plus B greater than 1. And all points in class -1 should be WTX plus B less than 1. Okay, good. So this is the, right, so we have a total of n constraints for n samples. Any questions on this? So let me ask you a question. Let's do a quick Piazza poll on this and see how people are. Okay, yeah, this is only one question. So yeah, maybe choose, as I always say, this is not graded, although this is actually a question that, you know, it's not trivial to do on the fly, but if you have time after class, you should revisit it and try to do it a bit more carefully and see the results and basically plug in the numbers and follow the same thing as we did, and you will see, hopefully, the outcome. It's, again, not something I expect you to do in the poll. The poll is just a very quick thought, and if you got it wrong, no problem. In exam or in problem set, you will have much more time to work. So don't, I just want to emphasize the point. That's why I asked this question, but if you didn't get it correct, don't feel bad. Okay, so let's talk about this and then move on. So I asked you a following question. Remember when I introduced the support vector machine optimization problem, I said that I'm selecting one as an arbitrary value. So I'm saying class 1 has to be greater or equal to 1, and class 0 has to be less than -1. But why 1? Why not 2? Why not 7? Why not 50, right? Maybe, you know, maybe 50 would lead to better margins or smaller margins and so forth. So the question I'm asking here is about changing 1 to 2. 1 is arbitrary. We could just as well pick half or pick 2. Why did we pick? What is the impact of changing that margin? And the answer to this question is actually answer 3. So the margin is not going to change, or the optimization function is not going to change. What is going to change? There's one thing that is going to change, and as I said, I mean, you should try, if you have time after class, to work this out, but I'm just going to tell you, and this is more or less what you should get. So when we did the optimization function, remember we ended up with this, M equals 2 over WTW, right? When you change 1 to 2, this becomes 4. But it doesn't matter, right? I mean, because really, the W that will maximize this for 2 over this will also maximize it for 4 over this, for 16 over the whatever. So again, the important thing is that whatever value you select does not make a difference, which is good, because that's a completely arbitrary decision we made. So it's good to know that it doesn't make a difference. Oh, but again, if you have time, you can work it out and see that this is the case. But this is good news, because then it means that we made an arbitrary decision, but it didn't affect the result that we got. Fine, okay. So let's go back to where we are and now start relaxing some of the assumptions that we made. So the first thing is, right, I mentioned already that, we ended up by saying that we can define a support vector machine as a quadratic programming problem. But remember, we made a very strong assumption initially about the fact that a line even exists between the 2 points, right? If a line doesn't exist, then it doesn't make sense even to ask which line is the best, because there is no line, so there's no margin. If there's no margin, we cannot define any, right? Right, in this case, there is no, if you look at this set of points, there is no line that separates the set of blue points and red points. So if there's no line, we can't define a margin. If we can define the margin, we cannot find support vectors, and we cannot define any line between these. So what can we do? And in fact, right, so we can say, look, we don't want to work on this type of problems, but unfortunately, in most cases, the data is not linearly separable. It's very hard to find a linear line or even non-linear line that separates the points perfectly, unless you're in very, very high dimensions. But in that case, you may actually overfit, and maybe it takes a long time, although that's exactly where support vector machines are powerful, but we'll get to that. But for now, let's assume that we work in 2 dimensions. We want one line, and we see that there is no line that will separate our points. Are we saying that we cannot use support vector machines, maybe use logistic regression, maybe use linear regression? The answer is maybe not. Maybe we can still find a line that, of course, does not completely separate it, but still provides a margin. How can we do that? What we should do is try to combine 2 things. One is the margin. We still want a large margin, But the second is also minimizing the errors. We know there's going to be errors because there's no linear separable, but we want to minimize those. So we want to have two things. One is still define a good margin, but second is minimize the errors. How can we do it? How can we combine these things? There's a few ideas. For example, we want to change our quadratic programming problem to say, rather than minimize, rather than require that everything is greater than, all class 1 is greater than WTX plus B is greater than 1, we can't require that, but we can say that we want to minimize the margin, maximize the margin by minimizing WTW, and also minimize the number of errors. So that's a good way to basically combine the two problems, right? On the one hand, we maximize the margin, and on the other hand, we minimize the error. Or another way is to penalize the number of errors. So maybe, we don't want to solve a double minimization problem because that might be very hard. Instead, we basically have a one minimization problem where we have some weight that we assign to the errors, and the goal is to minimize the combined number of errors and W with some weight on each one. Okay, these are definitely possible answers, and both combine our desire to maximize the margin, the WTW maximization or minimization, with our design to limit the errors. But both of them are not very good ways of really, right? Both of these are not good ways of, to define an optimization function. What's the problem with this definitions? Anybody can tell me a problem with this type of definitions that we didn't have before? Anybody can tell me, let's go. You can return to the quiz later, but now I asked a different problem. I asked, we want to minimize, of course, not minimize. We know there's no linear separable solution. There's no linear separable solution, and our goal is to try to find a solution that on the one hand maximizes the margin, while on the other hand minimizes the errors. And I suggested two options for that, either double minimization or some type of joint minimization of the number of errors and the margin. What's the problem with that? So of course the problem is it's not linearly separable, but that's by definition. But what's the problem with trying to optimize this type of function, right? So we have a target function. We want to minimize either the sum or what's the problem with minimizing this? All errors are treated equally. That might be a problem, but it's not the biggest problem. Anybody can tell me a problem with optimization of the function that I showed you? Think about other optimization functions we used. I didn't tell you how people solve quadratic programming, but it's the solvers assume something that this doesn't. So let's assume we have some. No. So I'm looking for something. Oh, good. Yeah, I see some answers along the lines. Yeah, so there's lots, of course, of problems with this. Of course, we need to make some arbitrary decision about C. That's true. That's a problem. By the way, that will be a problem going forward as well. But the real problem for optimization function is that the new target functions that I defined are not continuous. So they are not differentiable. The number of errors is a discrete quantity. Margin is continuous. It can go up, it can go down, but it's continuous. Number of errors, regardless if we do a double minimization or number, or is not continuous, right? If we move the line slightly, we change very rapidly from 0 to 1 in terms of the error. That's not something that is easy to optimize. Generally speaking, when we optimize something, we really would like a target function that is continuous, because we usually do a search. It doesn't matter if we do gradient descent or quadratic power. We do some search. If things change very rapidly in the search, then we can't really search effectively. So usually we would prefer, and that's true in this case as well, we would prefer target functions that are continuous. But again, we still want to have a target function that combines the errors and the margin. So how can we do it? So let's do what people implied in their answer and take into account not just the number of errors, but the magnitude of the errors. So let's define, in addition to the margin, so we have this boundary and we have the margin between the two planes that we defined. Of course, we are making errors, But now let's define the magnitude of the error as the distance between a point and the line that it should reside on the other side of, right? So for example, the blue point here should have resided on the other side of this line. So the error that we are making in this, when we use this line, is the distance between this line and the point. And similarly for this one. So we will call this epsilon k for this point, and we'll call this epsilon j for this point. And our goal will be to maximize the margin while minimizing the sum of the errors. Of course, if the sum of the errors is 0, then we make, and again, the important thing here is that we only take into account in this minimization the points on which we make an error, or the points that are on the boundary. Points here, these blue points that we make that are correct, are still not being used to compute, right? They are not, as we did in the original discussion, they are not affecting the boundary. The boundary is going to be affected by the points on the boundary, obviously, and the ones where we make mistake on. Okay, so this is the new optimization function. And it's slightly different because now we have, of course, the optimization for the boundary, and we also have a minimization term for the error. So epsilon is the error, it's always positive, it's the distance between a point and the line, defined as, you will see in a second how we defined it. And so, but it's always positive. And C is the weight. So we need to select an arbitrary weight, and our goal is to minimize. This is of course continuous, right? Because if I slightly move the line, the error moves slightly, right? It can change, but if it changes from, I mean, if I make it now not an error anymore, it means that before the error was very small because it was very close to the line. So this is much more continuous than, or in fact, this is fully continuous than before, much easier to optimize. The thing we have to do, of course, is now we should allow for errors. So we should require that all points in class 1 have WTX plus B greater or equal to 1 minus epsilon, where epsilon is the error term. For some points, epsilon is going to be 0 because they are on the right side of the line. We don't need epsilon for them. But for other points, epsilon is going to be a real number. So now epsilon becomes part of the parameters of our problem. Okay, before we only had W, it's important to understand. Epsilon is not a given input. It's part of the solution, right? We can still define this honestly, or not honestly, we can still define this as a quadratic polynomial. We'll get to that in a second, but you should understand that epsilons are now part of the parameters that the solver has to decide. Because once the solver sets W, it influences the epsilon. We don't know what epsilons are to begin with. We don't know where the line is. So this is part of the solution, not part of the input. Whereas, of course, X is the input and the class is the input, right? So 1 or minus 1. Okay, one other point is that before we said points on the boundary are support vectors because they define any points away from the margin basically are not support vectors. Now we have more support vectors. All the points on which we make error on are support vectors because they are going to affect the optimization function, which in turn will change W's. So these are also now support vectors. Not all the points are support vectors. Like the blue points here on the right side of the boundary, they are not support vectors because if I move this point here or here, it doesn't change the solution. But points that I make a mistake on, if I move this here, it's going to change epsilon. If I change epsilon, it's going to change W and so on. Okay, and also epsilon, of course, has to be positive, right? We don't, if we allow epsilon to be negative, then these points will also have an impact. We don't want that. We just want the ones we make mistake on. So epsilon has to be positive. And, right, for all so of course, if you are correct, then epsilon you set to 0, and by definition, you are correct. But if you are incorrect, you have to set epsilon to some positive value. Otherwise, these statements will be incorrect, but you are paying a penalty in the minimization function. So if you can set epsilon to 0, it's best because epsilon cannot be less than 0, and you pay a penalty for any value of epsilon. So if you can set epsilon to 0, then you set it to 0 from the optimization point of view, because this will be correct and this will be minimal. If you cannot set it to 0, your goal is to find an epsilon that is the minimal, so you somehow move the line so that you will decrease. So there is this trade-off between moving the line, which changes epsilon, but on the other hand, also changes the margin, right? Because it can be closer to one set of points or farther from another and lead to a bigger or a smaller margin. So this is the trade-off that we get from C, and C is arbitrary. So C is up to us to decide, and I will ask maybe in a second something about C, and also I think in the recitation you will see some discussion of C. You are free to choose C. The selection of C has an impact on the results, obviously. So if you change C, the results are going to change. And still, we have these optimizations. Just one point before I ask you a question. So this is also a quadratic programming problem, okay? So even though we added some terms, this is still a quadratic programming problem, right? Because now we have the quadratic term and the linear term. It's important to realize, though, that the matrix R that we said is not diagonal anymore. Why is that? Because the vector now is not W, it's W and then appended by epsilon. And for epsilon, we have all zeros because it's not part of the quadratic problem. Okay? So we have this vector of the solution vector for us is W, and below we append epsilon as another set of parameters for our problem. W is multiplied by a diagonal matrix. Epsilon, we don't have a quadratic term for it, so we leave that part as completely zero. On the other hand, now we have a linear part, which is 0 for all the W's. We don't need them, but it's C for all the epsilons. So this is still a quadratic programming problem, but of course, the matrix R and the vector D are slightly different because it's a different optimization function. And we have a slightly different set of, not a slightly, we have a different set of inequality constraints. Okay, so this is the nonlinear. So this is linear, non-linear. Both of them are quadratic programming problems. Or basically, you can feed both of them to a quadratic problem. Good. Okay. So now, yeah, we have more. Of course, I mean, this is only halfway for support vector machine because soon everything will change, but not in this lecture. So let's do another a short piazza poll on the impact of C. Okay, and as I said, you will see more on guess in the recitation and maybe maybe in the problem set. I'm not sure, but definitely the recitation we discussed. So let me open another poll and let's see if I can find it.
Sid, there's a quick question on Slack. Someone's asking where the point is when it's not on Slack. Sorry, in Zoom. Someone's saying where is the point when epsilon is equal to 1?
Where is the point when I say on the boundary? It could be any. In fact, epsilon. If epsilon, yeah, that's actually an interesting point. If epsilon is less than 1, if it's more than 1, then it's on the wrong side. If epsilon is less than 1, it's on the right side, but still inside the margin where we want things to be empty. So this could be the case. There could be things inside the margin. We don't want anything to be there, so we are still paying a price. But epsilon can be also between 0 and 1. So basically, we would be correct, but we don't want points there. Yeah, so this could happen. And if it's 1, it's exactly on the boundary. But still, it's not something we want because we want it to be on the other side of the margin, not on the boundary. Good. Yeah, okay, so let's say, I mean, we're running out of time, so let's discuss the poll. It's not a simple question, and I think it's, especially since we just discussed it. So again, I'm asking this as a poll. I would mention it anyway. So just a way of, introducing some break to the class. But if you didn't understand or if you don't get it correct, don't feel bad. I mean, this is really, we just discussed it and it takes some time to realize. But let's go and discuss this question. So I asked, what's going to be the impact of C? I said already, C is arbitrary. We decide C, and it's a way to weight the maximization of the margin with the reduction in error, right? So C is multiplying the effect of the errors. And the question is, what happens when we increase C? So when we increase C, right, we are doing a minimization science. So when we increase C, we put more emphasis on the errors. When C is very low, when C is 0, for example, we don't care about errors. When C is very high, we care a lot about errors. In fact, we want to minimize the errors as much as possible, even if it comes at the expense of the margin. So I was asked before, what happens when the error is less than 1? Let's say it's half. If it's half, it means that the point lies between the +1 plane and the boundary. We can actually make this error disappear by moving the line right? They're moving the +1 plane towards the boundary. In that case, the point suddenly will be on the right side. So the error will disappear, but the margin will shrink. So this is exactly the trade-off. Now, when C is very high, we will minimize the number of errors we are going to make, or we'll try to minimize as much as possible. This means that most of the points we will try to get correct, they will be on the right side of the boundary. Any point that is on the right side of the boundary is not a support vector. On the other hand, points that are mistakes are support vectors because they are affecting the answer. So the answer for this is when we increase C, we put more emphasis on errors, so we try to reduce the errors. When we reduce the errors, we reduce the number of support vectors. So the answer in this case is 2. Okay? And again, hopefully in the recitation, you will go through some visual examples of I think, and we'll try, of what happens to the boundary when you change C. Okay? Or if not this week, next week, because this should be tied with what I'm going to talk about Monday. Okay, again, so if this is not clear, you know, take your time, go over the definition again after class. And that's basically it. Next time, we are going to talk about, we're going to continue about support vector machine, but introduce a completely different way to solve it. It's still the same optimization function, but different way of solving it. And we'll discuss why this is a good idea and what it gives us. Okay? So yeah, I'll see everybody on Monday.